Okay, so this is just going to be an introductory video into solutions to systems of linear equations and how we can solve them via graphing. So, first things first, at this point you should be or have learned about just this y equals mx plus b, so we're going to talk about this very quickly. So just as a quick refresher, remembering that m represents your slope, okay? But more importantly, okay, when graphing, you're going to want to know that that is this delta y, which is this change in y, all right, divided by this thing that we call delta x, which just represents change in x, okay? So in other words, what you have is that you have a y coordinate that goes up or down divided by an x coordinate that goes right or left, okay? So that's an important piece for graphing. Okay, so then b, what does b represent? So b represents the y-intercept. All right, so the y-intercept, comma, it is the when x equals 0. Okay, so that's the important thing. So what do x and y represent? So x and y represent a coordinate pair. Okay, that is just simply, okay, on the line. So that's an important piece. Now, while x and y represents a coordinate pair on the line, I also want you to remember that this y value is just an output, okay? So when we talk about it in the sense of the equation, remember that that y is an output, and then this x, okay, I'm not pointing to the m there, so be very careful. I'm just pointing to the x as the input, all right? Because most equations are going to have some output based off of something you can do to an input, all right? So important skill is let's verify solutions, right? Number one, being able to verify whether a point exists on on any given equation, all right? To do this, all right, we simply, okay, we plug, okay, the point into the equation. Okay, so you plug the point into the equation to determine if the coordinate makes a what we call a true, okay, or a false statement. So basically, if it is a true statement, then the point does exist on the graph of the line that I'm checking. If it produces a false, okay, statement, then the point does not exist on the graph of the line. So let's just go through two of these very quickly, just to talk about going through and what it means to verify a point. So after we've ran through some of this basic review, then we can start getting on to graphing of lines, okay? So number one, does the point for -2 exist on the line of y equals 1/2 x minus 4? So in the notes you just took, if you look at it, it simply says just to plug your point in. So what you need to remember though, right, is you're talking about coordinate pairs, right? So this is your x, this is your y, so input, output. So in this equation, I just plug the input and the output for where they're supposed to be. If it's a true statement, it's on. If it's not, it's false, okay? So here we go. Let's just test it. We're just going to do some substitution. We're going to plug it in. So wherever I see a y, I can now write -2 equals. So 1/2, that doesn't change. It's still in the original problem, okay? And wherever I see an x, when I use substitution, always use parentheses, okay? So times 4 minus 4. Now the goal is just to check, is this side actually going to make the value of -2? Because if it does, then I have a statement that says -2 equals -2. So let's just check. So what I get is -2 is equivalent to, well, 1/2 of 4 is 2, so this becomes 2 minus 4. And well, 2 minus 4, okay, is just -2. So what I have here collectively, we look at this whole statement, and you ask yourself, does -2 actually equal -2? So this is like saying to yourself, is -2 -2? So the answer to that is yes, and that's what we call, okay, a true statement. So the above statement is true, so therefore the point does exist on the line. So this is just verifying whether a point is on a line or not. But the skill that we're going through is very, very important because this skill is actually how we are able to graph lines, and I'll demonstrate what I mean in a second, but let's just go through and look at a false statement now. So now you have the true, let's take a look at the false statement. So here we go. So the false statement, here it goes. So remember, this is y, that is x, so your coordinate pairs comes x comma y, so wherever I see a y, okay, I can now write 3, so I'm going to write 3. And then I'm going to write equals, and then this is a 2, and wherever I see an x, I'm going to put parentheses around it and put a -5, so 2 times -5. And then I get this plus 7. So now what I'm observing, I'm checking, does this side right here produce the value of positive 3? So this side now is 3 equals, well, 2 times -5 is -10, and -10 plus 7 is close looking, okay, they're similar. However, the right side is -3, okay, and the left side is positive 3. So what we say is this is a false statement. They are not equal to each other. Things that are not equal to each other are false statements. So what we have is a false statement. So because we have a false statement, what I would say is the point -5,3 does not, okay, so this is a does not exist on the line. So I hope you understand what's going on here. At this point, we're just plugging points into an equation to remember that you have inputs and outputs, and in this case, we're just verifying if it's an equation of a line. So now let's talk about how does this skill transpire and move forward into how do we graph a line. All right, so continuing on with this idea, okay, we're going to move into what we call systems of equations. So we were just talking about linear equations, and we were talking about plugging points in and talking about how does that help us graphing lines, and we're going to get there. That skill is important. It's coming up. It's coming up in the next couple of notes here, but we're just kind of honing in on this idea of what does it mean to be a solution. So what we just found out before was that we plugged the point in and we found out if that point was on the line or not. So what we have going on right now is we have systems of equations. So a system of equations is a single coordinate plane that has, okay, 2 or more linear functions graphed on that same plane. So what we're now going to be looking at is not just one, or thinking about one line on a graph, we're going to be thinking about multiple lines on one graph. All right, so that's where we're going with this. So what does the solution look like? What is it? Well, we're on a coordinate plane. So guess what the solution is going to be? Well, the solution is just going to be a point. Okay, it's going to be a point, and that point is going to be x comma y. All right, so that when you evaluate it by both of them, okay, so when I evaluate simultaneously, all right, so both equations are going to produce what we have as a true statement. So now that's important because I'm talking about simultaneously. And if you don't know what simultaneously means, that word means both. Okay? So, which means the point is, okay, on, okay, the graph of each line. Okay, so that's an important piece there. So, what we have going on now is this idea of we're taking this idea of plugging a point into an equation and seeing what happens, okay? So now that we have a system of equations is just going to be 2 lines. If I have 2 lines, I have 2 equations, and the solution is going to be that point that I plug into both equations that both produce a true statement for. All right, so that's basically what the first part I just talked about was. So now, common phrases. So just so you don't get tripped up, all right? Does the point satisfy the system? Does the point solve the system? Is the point a solution? Find the answer to the system. These are just all common ways of asking the same simple question, okay? So what we're about to do right now is we're going to use, okay, a way to check that when we actually do start graphing these to check, all right, our work to see, hey, does this point actually work? Did I graph this thing correctly, okay? So here's some examples. We're now going to check whether the points that I have in here in these problems are actual solutions to my system. So algebraically, what we can do is we can just do what we did before. We simply plug that point, okay, into your equations. Now, a common mistake, you can't just plug it into one, all right? You gotta plug your equation into both lines. So you're going to have to plug that point into this first one, then you have to plug that point into this second one, okay? And what you will need is you will need a true statement from the thing that I highlighted in blue, and you will also need a true statement from the thing that was highlighted in green, and that's a very, very important piece there. You need to have 2 truths, okay? If this does not work for both, which what I stated above before, then it's not a solution. You need to have it work for both, okay? So let's show you what a true statement looks like versus what a false statement would look like. So here we go. Now, whenever you plug a point in to a system, okay, into an equation, so I'm going to plug it into this first one here, all the numbers, all the signs stay put. The only thing you're going to swap out is the variable. So notice I'm going to place a 2 down here, okay, and then I'm going to put parentheses. So parenthesis, parenthesis, plus 5. I'm going to swap out that y, parenthesis, parenthesis, equals 14. So what you should notice is that this equation right here that I wrote down below looks very similar. And now what I'm going to do is I'm going to go back and I'm going to plug in, okay, my 2 values. So above, okay, above, remember we had that this value here was x and that this value here is y. So what I'm going to do is I'm going to go down and plug them in. So in this first spot here, it said 2x, so that's 2 times negative 3. The next spot said 5 times y, so I'm going to do 5 times 4. And all I'm going to evaluate is, does this side actually produce the value of 14? So 2 times negative 3 is negative 6, plus 5 times 4 is 20. And does that equal 14? Well, lo and behold, negative 6 plus 20 is 14 equals 14. So check, that works. I have a true statement going on in the first one. Go to the second one, right? So the second equation is y equals 2/3 x. So if you want to, here we go. I'm going to put a parenthesis, equals, so 2/3 parenthesis plus 6. So notice that you see wherever there was a y or an x, I put a parenthesis. So now I'm just going to go back and I'm going to plug my values in. Where there was a y in the second equation, I plug a 4. And wherever there was an x, I place that negative 3 in. Okay? So if you notice here, very important piece here, do you notice how I plug this negative 3 into both equations? It's not like I'm using different numbers. These numbers should match. Okay, and notice I'm plugging them in for their corresponding variables. Y's get the y, y's get the y, x's have the x's. That's an important piece there. So all I'm going to do is I'm just going to go ahead and evaluate this again. So I'm just checking for, is that equal to? Well, 2/3 times negative 3 is negative 2 plus 6. Well, does negative 2 plus 6 indeed make 4? And the answer to that is yes, 4 does equal 4. So the point works for both equations. So since it works for both equations, okay, for the point, okay, so therefore the point is a solution, okay, so it is a solution. So that's an important piece. So that point, negative 3, 4, is a solution. So moving on to what a false statement would look like. So a false statement, here we go. So again, we do the same thing. So in your problem, you may want to highlight, okay, your point there. So my point is 1/2 6. So what I'm going to do is I'm going to go through the same process, okay? So wherever I see a y, I plug a 6. Wherever I see an x, I put a 1/2. So here we go. So the first thing I'm going to do is parentheses. Oop. Okay, so for the sake of time, I kind of set this up already and pre-filled it in. But what you should notice is I'm just going to be plugging the numbers in. So I took the values from above and I plugged them in. So all we're going to check now is, does 6 equal, so 8 times 1/2 is 4, so 4 plus 2 is, well, 6 does equal 6, so check. So it does work for the first one, okay? But when we go to the second one, we're still going to check. So 4 times 1/2 plus 6, does that equal 10? So 4 times 1/2 is 2, so 2 plus 6, does that equal 10? And 2 plus 6, we're just checking, does that make 10? The answer is no, it makes 10, it makes 8. So 8 does not equal 10. So what you have now is we have got this thing called a false statement. So what you have is because the point works for one equation and not both, all right? So therefore the point, okay, is not a solution. So remember, for it to be a solution, it has to work for both, okay? So that's an important thing. So now, we've done all of this stuff algebraically. Let's go get a good visual and look at what we're doing, all right? So here we go. So, system of equations. So that first top line again, I'm literally going back through this because this top line, this top little piece area is the most important to understanding what you're looking for. It's what you need to remember for a system. So again, if you remember, a system of equations is just two or more, okay, lines on one graph. A solution is a point, okay, x, comma, y. All right, that when given will both produce a true statement. So the important thing here is both, all right, which means the point is on the graph of each line, okay? So we're going to take a look at this stuff visually really quick. So what you have here is a system. So this is the things that we're going to be graphing in a second. And what we're going to do is we're just going to pick what the solution is. So notice, we have two lines, and I got to find a point that is on both of those lines. Well, if you just plot some random points here very quickly, okay, so if I plot a point, here's a point on this line. My question to you is that point that I just plotted on this line and this line at the same time? So that's what it means simultaneously. So wherever you are, so yes, this point is on that line, right? But it's not on this line. So basically, think about what we're looking for on this whole picture. We're looking for the place that they intersect. So if I plot that point where they intersect, all right, boom, there it is. They then have the solution. That point, if you notice, I could say is on the red line, or I could say it's on the blue line. So that's because it's on both. So the solution to this is the point -2, -1, right? So that's an important thing here. Okay, the reason -2, -1 is a solution, okay, is because, all right, the point is on both lines, okay? So just hammering home this idea of a solution. So determine the solution of this next one. So we take a look at this next one, and it has the point graphed for me already. So I just need to figure out what that point is, and that point is the point 1, 3. So right now we're just talking about coordinate points, and what we're beginning to recognize is that thing we were solving for algebraically before is actually the intersection point of these lines. So the reason the point 1, 3 is a solution to the system is because, again, the point is on both lines. Now, the thing that I just said there that was kind of important, that yes, so what is in common between the location of the solution? So we know that the point is on both lines, and the location of that point is the point is where both lines intersect. All right, so that is called the intersection point. This is called the intersection point. So we've done a whole lot right now, and we have yet to graph a line. But the point of this is because we are going to be asking you to solve a system of equations by graphing. So just graphing something doesn't mean you've solved anything. So what we are really hammering home here is this idea that when you solve a system, that after you graph it, you should be looking for a point where both lines intersect. All right, that's an extremely important topic of idea. You don't have a solution if you don't find that intersection point. So we need to find that intersection point. So now let's get into graphing these now that we have an idea of what the solution is and how you get it and where it's found. So here we go. So moving forward. So we use this method for solving systems if and only if, okay, both equations are in what we call slope-intercept form. And that form is y equals mx plus b. So you can only graph a line if it's in y equals mx plus b. All right, so that's an important piece. Now, how you graph a line is up to you. I'm going to show two methods of how you graph a line. In number 7, I'm going to use an input-output table. In number 8, what I'm going to use is this thing called slope triangle. What you need to decide is which method works for you and which method do you pick up best, okay? So what I'm going to do is I'm going to make an input-output table for this, and I'm just going to label it A, okay, and I'll label this B so that you know which table is which one. So, to graph a line, it's pretty simple. It's actually really easy to do, all right? So what you're going to do is you're just going to plug two numbers in and get two numbers out. Remember how I talked about in this equation, y equals mx plus b, that x was an input and y was an output. So all I simply need to do, so I'm going to call this table A, and I go x, y. And all I need to do is pick an input. So I look at the first equation, it says y equals negative x minus 3. So what I'm going to do is I'm going to plug in just two numbers for x. And then I'm going to calculate what the y would be. So I'm going to plug in this number 0. So why do I use 0? Well, remember that the b was when the x coordinate was 0. So I always, no matter what table I use, I always want to plug 0 in. The next point that I plug in will always be the denominator of slope. So in this case, all right, my first equation has a negative out front. So remember that that's a negative 1. Well, mister, you just said the denominator. Well, yes, any number can be written over 1. So my denominator that I will use is 1. So couple things to note here, that if you don't have a fraction out front, you're always plugging the 2 points 0 and 1 in. So all I'm now going to do is plug the point 0 and plug the point 1 into my equation. And that's it. So here we go. Just to demonstrate this, the line is negative, so 0 minus 3. So negative times 0 is 0, so 0 minus 3 is negative 3. And the next time I do this is negative, okay, 1, and then minus 3. So negative 1 minus 3 is negative 4. So now I have my 2 points. So now what I'm going to say to you is we always finish it off. We don't go to the second one. Don't make the table for the second one. Plot your points now. Okay, so my points are 0, negative 3, and 1, negative 4. So 0, negative 3, and 1, negative 4. I have my 2 points. And once I have my 2 points, what I'm going to go ahead and do is I'm going to go ahead and I'm just simply going to graph it. Okay, and that's it. So here we go, graphing my line. So there's the first one. The first line is done. So this is line A, okay? So then I'm going to go to line B. So same thing, I'm just going to make my table. So here comes line B. So here we go. So table, so x, y. And again, notice I don't have a fraction out in front of x. So, and I don't even have a number there. Well, yes, I do. I have the number 1, right? So here's the deal. If you have what appears to be no number or no fraction, you're always using the point 0, 1. Pretty simple, okay? So here we go. 0, so plug it in. So 0 plus 1 is 1. And then you have the next thing, which is 1. So I'm going to plug in a 1 plus 1, and 1 plus 1 is 2. So, hey, lo and behold, I now have 2 points, and I'm just going to go ahead and plot them. And I'll plot them in a different color here for you. So here we go. So the method that I'm doing right now is just an input-output table. That's it. So here we go. I got the point 0, 1, and I have the point 1, 2. And all I'm going to do is I'm going to draw through there. So here we go. So there's my line graphed. And then remember, what I'm looking for is the point where my 2 lines intersect. So what I highly suggest is that you are going to use a ruler, okay? So if you notice, this is my point of intersection right here. And that point of intersection is the point negative 2, negative 1. And then there's my solution, okay? I'm done. So that's it. That's all you have to do there. So now notice the first way I did this was kind of long, all right? So what I'm going to show you now is this other method that does make it a little quicker, and this is called slope triangles. Now, what this other method, so number 8, so you should look over at number 8 really quickly, is going to utilize m equaling this delta y over delta x. And it was one of the very first things I talked about. So what you have is this thing that can go up, or you have this thing that can go down. If it's up, it's positive, down is negative. So what you have is change in y over change in x. Well, if you go to the right, it's positive. If you go to the left, it's negative. So what I'm going to do is I'm going to steal the fraction out in front of x, or the number out in front of x, and I'm going to write it as a ratio, okay? So here we go. The first thing I'm going to do is in this thing, I'm going to say m. What was m equal to? Well, m in this case is 3 halves, and they're both positive 3. So what that means is that I now have this value of going up 3, and it's a positive 2, so I have it's going right 2. Now, that's great. I go up 3 and I go right 2. From where, right? And that's the last piece you need to know. What is your starting point? And your starting point is this value in your equation. So negative 3, that is b. Remember, b is your starting point. So what I'm going to do is I'm going to plot the point 0, negative 3, and then from there I'm going to go up 3 to the right 2. And that's what we call slope triangle. So here we go. So I plot the point negative 3, and then from there I utilize the directions. Go up 3, so count 1, 2, 3, and to the right 1, 2. Plot a point. Now the nice thing about slope triangles, it allows you to get a bunch of points pretty quickly because I just follow the same directions. Up from this point, 1, 2, 3 over 1, 2, plot another point. Up 1, 2, 3 over 1, 2, plot another point. So what you notice here is that I get a bunch of points. Now what about the points over here to the left? Well, over here to the left, it's pretty simple. Go in reverse of how you got to this point and just go backwards. So down 3, left 2. So down 3, left 2, and I can plot a point. So I go down 1, 2, 3 to the left, 1, 2. Okay, down 1, 2, 3 to the left, 2. There we go. I have my line, and there we go. It's in and it's drawn. Boop. There we go. So going on to the next line, again, the important piece of what I'm doing, all right, is going to be first getting m. So recognizing m is negative 1 over 4. All right, so that means I must go down 1. And I go right 4. So again, I'm assigning the arrow to which direction. So down 1 and to the right 4. Now again, well, where do I go down 1 and to the right 4? Well, you go from your starting point, and your starting point for the second line is at positive 4. So I put a point at positive 4, and from there I go down 1 and then 1, 2, 3, 4 to the right. Whoop, there we go. So what I now have is I have my line that goes through. And what I've got is my intersection point right here, and that intersection point is the coordinate pair 4, 3. Okay? And then there you have it. That is the end of this video. We have got this idea of graphing a line, and that's it. So choose and go back through this. Which method do you like? Do you like the input-output table, or do you like the slope method? It doesn't matter which one you use, but you know what, for the sake of this video, one last thing I'll do is I'll go through and I'll show you, hey, well, let's pretend I liked, just for a second, let's pretend I liked that table value A. Well, what do you mean the table value A? Why? And I want to go through the table quickly, just a little differently here. So again, we'll call this equation A and this equation B, and let's make a table for this. So notice what I said before is that I'm going to use 0 always, so in my table, so here's the table for A. Okay, I'm always going to use the point, so x and y, I'm always going to use 0 for x, and the second number I'm always going to use is always going to be the denominator of my fraction. So it will be 0, 2, okay? And then all I'm going to do is plug those points in. So 3 halves times 0. So 3 halves times 0 is just 0. So I'm just doing this. 3 halves times 0 minus 3. Well, 3 halves times 0 minus 3 is just negative 3, right? Which, if you notice, this number here should always match b. 0 should always match what the b is, right? So that's an important piece. So then the next one is just going to be 3 halves times 2 minus 3. Well, 3 halves times 2 is 3. And 3 minus 3 equals 0, so my y value is 0. So what I now get is a coordinate pair, 2 of them. So I have the first point, which is 0, negative 3. And the next one I have is the coordinate pair 2, 0. Okay? And then I'm done. I can go ahead and graph my line. So there it is. So notice I had that line before. I'm just graphing it this way using a table. So the table that I used the first time had 0, 1 in it. This one has a 0, 2 because I'm strictly choosing always the denominator of slope for my second point. So this is the input-output way. So here we go. Let's just do B. So B, here we go. Making a table. X, Y. So the point I always plug in is going to be 0. And the second x value I always plug into this equation is going to be the denominator, which is going to be 4. Right? So the denominator is 4. So I'm just going to plug those points in. So I'm going to get negative 1/4 times 0 plus 4. So 0, okay, because 0 times anything is 0. So 0 plus 4 is 4. And then I go negative 1/4 times 4 plus 4. And then I get negative 1/4 times 4 is negative 1, and negative 1 plus 4 is equal to 3. So my next point is 3. So if you notice here, I get that same point. So I get the 0, 4, and I get the point 4, 3. All right? And what you have here, okay, again, just going back through this. This is just the second time I'm doing this. I'm just doing this one now with the slope, okay? Not without using slope, sorry. This one, I'm just using the input-output table. So I hope you're, by now, picking one method that you liked over the other. But either way, the solution to this system is still the point 4, 3. The solution to this particular system, again, when we looked at it, was the value of negative 2, negative 1. All right, so that is how you graph a system of equations and solve it.